Hello, geology students. Today we're going to talk about fossil succession and how we use fossils to develop the geologic timescale. So looking at human time, this is kind of a typical breakdown, right, for our history, millennium, century, decades, going all the way down to seconds. Geology is talking about much broader amounts of time. So we break it down a little bit differently into eons, eras, and periods, and you can go smaller than that. I really want you guys to try to remember the eon, era, and period denotation or breakdown, and the easiest way, I think, just alphabetically, E, O, E, R, and then P if you're trying to remember from big amounts of time down to smaller periods of time. So looking at the geologic time scale, we have 4 eons of geologic time. Okay, we got Hadean, which is the hidden eon. Now the hidden eon this is when the Earth was forming, right? And it's called the hidden eon because we didn't really have even rocks forming at this point, or just starting to form. So we don't have a lot of evidence, or not a lot of physical record of this period. Okay, and Hadean, you can think of like Hades, as in hell, as in it was very nasty on Earth, right? So the Earth was cooling, getting bombarded by meteors and comets. So it was not a real good time. Okay, the Archean is the ancient eon. Okay, so this is when Earth was cooling. At this point, we're starting to get the development of oceans on planet Earth. Proterozoic is where we have early life. So this is going to be your, certainly not any kind of fancy life like we see now on Earth, but you're going to have some very simple life forms on Earth. And then the Phanerozoic is visible life, and this occurred at 540 million years ago. And this is when life really exploded on Earth and got very complex. It really started to diversify. Okay, so the 4,600 million years ago, that's 4.6 billion, 3.8 billion, 2.5 billion, and then 540. So those are the 4 eons of geologic time, so big sections. So if we look or break that down and try to see how it appears on, this is our geologic time scale, much more complex one that's got a lot of information on it. Here are your eons. Okay, so there's your Hadean, Archean, and Proterozoic eon over here on the right. We kind of classify or group those together in what we call the Precambrian. Cambrian is right down here. So this was Precambrian. And then the Phanerozoic, okay, the visible life, kind of where we are right now, is that whole section on the right there. So we've got a lot more information about the Phanerozoic eon. That's why you see it's so much larger compared to the other ones. Okay. All right, then, if we look at the eras, okay, the eras on the right here, are listed there. That's for those Precambrian ones. And then all of the other eras that are during the Phanerozoic are that we've got the Paleozoic, which is old life, Mesozoic era, which is middle life, and then Cenozoic, where we are, is recent life. Okay, so those would be our eras. And then lastly, we get into the periods. The periods are the much smaller sections here. And these you might have even heard of before. You've got Cambrian, Permian, maybe you've heard of, Triassic, Jurassic, Cretaceous, most people have heard of those, Paleogene, Neogene. Okay, so when breaking down where we are right now, we are in the Phanerozoic eon, right? And we are in the Cenozoic era, right? And then lastly, we're in now the Quaternary period right up here. And if we got even smaller, the Epoch, we're in the Holocene. Okay, so that's what's happening here. If you look right here, there's the Pleistocene, that's the Ice Age. And so we talked about that in class. All right, so what records the passing of geologic time? So rock layers we've talked about, sediments are deposited over time in layers, and we learned about those in our different principles of, like the principle of superposition, etc., right? So those layers trap and record information, and those layers are analogous to pages of a book, right? So it's kind of the idea of each layer is recording information. And the Grand Canyon is a great example of this, okay? So with the Grand Canyon here, we've got all these different layers, and we learned about in those different principles, right, that we can determine the different rock types, right, when they were deposited, and that's going to tell us maybe how they were deposited in an ocean environment or beach environment. Was the water getting deeper? Was the water getting shallow? We can record all that. And again, in that way, these layers act like layers of a book or pages of a book. So But when we're trying to figure out the order, right, in a book you've got page numbers. It's all just laid out that way. But how do we determine the order in which the rock layers form? Now, at a single location, it's pretty straightforward because we can just use that principle of superposition, right, with the oldest on the bottom and the youngest on the top. Okay, so that's relatively easy for us to be able to figure that out. Now, even if we have a regional area, right, we can correlate two different areas based on their lithology or the physical characteristics of the rock layer. So, for example, if we look at the southeast coast of England and the northwest coast of France, they're relatively close, right? They're in the general region and they're just separated by the English Channel. And those rock layers, they will match up, right? So we can kind of correlate these two locations to each other based on their similar lithology or the rock layers being about the same. So this is a map just showing that, and this is one of those original ones, and this is what they were actually able to do and how they started to think about all this stuff, because they had over there in Europe this chalk deposit, right, and it matched up from, you know, France and Germany and Poland, this whole area, going over into Great Britain, right, up into England there, and that's that chalk layer. So they were able to kind of connect the layers. But we have a problem when we look on a larger scale, right? Because now we have North America way over here, and you've got England and Africa, or Europe and Africa over here. So you're talking about a much greater distance. So the rock layers are not going to match. You've got the mid-ocean ridge going down the middle here that's creating new rock, new seafloor all the time. So the rock layers are not going to match up. Okay, so that becomes a problem, right? Because if we have these different layers between North America and continental Europe, we can't correlate them based on their physical features, right? Because they're going to be different rock types, etc. So this guy, William Smith, came along, and he was a surveyor and a civil engineer. And he started to do some research, right? He was going all around. And he made the first larger scale geologic map that showed the distribution and kind of these different rock layers. So he's going around and he just kind of recorded all this information, right? And in his work, what he discovered or noticed was that the rock sequences seemed to contain kind of a unique pattern of fossils that would appear and then disappear. Okay? So even when the rock layers were different at different locations, the order of these fossils was always the same. Okay? So where you would have a fossil show up and then it would disappear, and then a different fossil would show up and then it would disappear. And that order, that sequence was always the same. Okay? So, how do we assign sedimentary layers to their correct place in time? He was really instrumental in the concept of index fossils. So what index fossils are a unique set of species that existed during time. And knowing that species evolve, live for a short period of time, and then go later going extinct. So this is that idea of that we have these fossils that only exist on Earth, right, for a certain amount of time, and they never disappear and then reappear in the same way. Okay? And that allows us to then kind of zone in or narrow in onto a specific amount of time if we can find when these fossils or when these creatures lived on Earth. So this process of evolution provides a biological calendar that geologists can use to keep track of time. So these fossils allow us to put these scenes from Earth history in the correct order. Because if we find a fossil, we know when it existed on Earth. So wherever we find that fossil on Earth, it's going to help us out. So here's that concept shown in pictures. Okay, so you've got time going on here, and we know species evolve, they live on Earth, and then they go extinct after a certain amount of time. Okay, and that continues on for all kinds of species. Lots of species have existed on Earth and then gone extinct. Okay. Now, if you find the rock layers, then we can then kind of make connections to figure out how old a rock layer is. So, for example, this first one at the bottom here, if you only find this fossil, we know that it would correlate to whatever time period that fossil was on Earth. Now, if you have this fossil and this other species both in the same layer, that means they were living or dying or being deposited on Earth at the same time. So, and this species here went extinct while this one was beginning to evolve. So that tells us something very important, right? It allows us to determine how old this rock layer is, okay, based on how these species have evolved over time. So fossils then are going to be the key to correlating regional systems. So if we're looking at North America and continental Europe, the rock layers may be very different, But what we can do is use fossils to find out when these rock layers were deposited at the same time. So look at this picture right here, and can you identify the rock layers that correlate to each other or match up based on the fossils? All right, what you should see is that right there, right? You see, notice how this group of fossils here matches the group of fossils here. So even though they are thousands of miles apart and in maybe a different type of rock, we know that those species only existed on a certain time on Earth. So if they were found in two locations, those rocks must have been deposited around the same time. Okay? So once a particular regional system was named, all these fossils kind of got correlated and grouped together into the same name. So, for example, the Jurassic system was named for the rocks and fossils that were found in the Jura Mountains between France and Switzerland. So any rock layers with those fossils are identified as being Jurassic in age. And that then allows us to develop, right, this geologic time scale where all of these little sections and all these little periods and epochs and ages, and these are all based on these defining events, right? When a species showed up on Earth, when a species went extinct on Earth, when this rock layer did this, when this rock layer did that. That's how this is all broken down. Okay? All right, if you have any questions, shoot me an email, rewatch the video, or stop me in class.